Okay, so we went over a couple things dealing with air resistance. We dropped a marker. This will not fall as fast because of air resistance, okay? There's four forces we talked about: gravity, strong, weak, electromagnetic. Okay, now, like we discussed in the morning session, this desk here, it's not moving, but there is wheels on the floor. As you can see, we can move this. Okay, but if it is not moving, what type of friction might that be? Is it sliding, gliding, static? Yeah, static friction because it's not moving. Okay, so one of the things we talked about is if you wanted to see maybe the Great Pyramids in Egypt, and yeah, you're probably picking up on some of the construction outside. They had to move really large blocks of sandstone from the quarry to where it was going to be built. The wheel hadn't been invented yet. So would it be easier to push this large block of sandstone on the ground or put it on a sled? Put it on a sled. It's not very efficient, but it's better than trying to push that on the ground. So if it's not moving, again, what type of friction is that when it's not moving? Static friction. But then once this does start to move, this sled, it's coming in contact with the ground and it is just moving across the ground. So that's sliding friction there. That's right. Okay. So if you are, how do I want to say this? When you're hitting the volleyball, maybe passing a little bit, throwing a basketball or passing it or throwing a football, when you throw that, does it travel in a perfect horizontal line like this? I mean, it will for a while, but eventually what's going to happen? Yeah, well, it could get caught too, but it's going to hit the ground. So, especially in football, if you are throwing a long pass, do you throw it like this, or would you put a little bit of arc to it? Why would you want to put arc on it? Because if you try to throw it like this, it might not get far enough. So you have to, the object wants to travel in a curved path, okay? Just because gravity is acting upon it, okay? Then we talked about this as well. Hunting. It was for in-state residents 2 weeks ago. Then last weekend it was for out-of-state hunters. Anyone do pheasant hunting over the weekend? Okay. How many of you have shot a rifle or a shotgun before? Okay. So if this is your buttstock right here, okay, so you got your gun. What happens if you pull the trigger and there's a little bit of a gap here? It's going to come back like this, isn't it? Okay? It's probably the only time you ever make that mistake. Okay? Because otherwise you want to pull that tight or hold it close to your shoulder. So once you pull the trigger, if the projectile is moving down the barrel, why is it moving back this way, the gun? Yeah, because it's an equal and opposite reaction. So would that be Newton's first, second, or third law? Second. Actually, the third one. Because inertia, that's the first law. Okay? When cars go around a curved path, the inertia wants to push it, keep pushing it forward. That was Newton's first law. Newton's second law, then, is this. Force equals ma, or mass times acceleration. That's Newton's second law. Then the third one is forces come in pairs. They equal in opposite directions. Okay? So if there was a slant, or if this parking lot, well, is on a hill, your car is not moving. So the tires coming in contact with the ground is what type of friction again?
Static.
Yeah, it'd be static friction. That's right. Even if you're parked on a hill or an incline or even on a flat surface, okay, tires are not moving, come in contact with the ground, so that is again static friction. So what we talked about this earlier, what stops your vehicle? Is it the brakes or is it the tires?
The brakes.
Okay? It's actually the tires. Because and this has happened while on the bus route. I sometimes have to remind the students to stay in their seat, because what may come running out of the ditch right in front of you? A deer. So there's a couple things to do, okay? Obviously in a bus you're going to try not to swerve. So same thing would occur. You just, okay, you try to slow down if possible, but otherwise you just plow straight into it, okay? But if you can slow down enough, yes, go ahead and do that. But should you lock your brakes up, okay? Well, you hope not. But should you lock your brakes up, is it the brakes that are stopping the vehicle, or is it the stopping of the tires and then the tires coming in contact with the ground that stops the vehicle? Yeah, the tires coming in contact with the ground is actually what stops your vehicle. Okay. And then keep in mind what your different forces were or are, okay? Of course, there's gravity. That just means two objects are coming in contact with one another. The electromagnetic force deals with tiny, tiny particles, okay? But then what was the strong force? We saw that in the video yesterday as well, okay? What I mean by that is if you have a nucleus of an atom that has all of these protons and neutrons together, okay, we said the first atomic bomb. Does anyone know what happens with an atomic bomb? You're splitting this, actually. And when you split that, you are given an enormous amount of energy, okay? I mean, enough to wipe out entire cities, city blocks, okay? But that doesn't explain this strong force in the center of the atom. It does something with the protons and the neutrons. They can't escape, but yet they don't collide with one another. That's what the strong force does, okay? All right. Then we also had discussed, okay, so if we were looking at a tire here, and I think this structure is actually called a dynamometer, okay? So when you balance your tires after you put a new tire on, it's a little metal clip that they'll put inside in the hub or the rim. And when they spin that on there, that's called a dynamometer. So the wheel's moving, but it's not attached to anything except the apparatus. So the wheel's spinning, but it's just not going anywhere. So if we have this on, and we call this point A on this circle, okay? And we've got this rock moving, okay? So then as this is moving in this circle, this rock lets go right at point A, okay? So the resulting force, would that be this? Would it be this? Would it maybe do that? Or would it maybe do that? So it's moving around this circle. Remember, you got centripetal acceleration moving here. Then if it breaks right here, or that rock lets go, or if this is a rope, then there's rock attached. Right here is where it lets go. Is that rock going to move this way that way, straight up, or straight down, do you think?
Down. Down.
Remember, what does centripetal acceleration do? It's acceleration towards what? Towards the center, correct?
So down.
So it would be this one, right here. Okay? Even though you have this moving around here, you might think that it's going to do this if it breaks off here, but that centripetal acceleration is holding that rock towards the center, and even when that happens, it's going to make it move in this direction. But what happens if it lets go about like right here in this vicinity, past point A? Then what way might it go? That's going to do this one. So if it's at point A, it's going to shoot that way. If it's past point A, like what we see here, it's going to shoot that down. Now, the reason that you might think, well, you might not think this, but the reason that it's important is when you look at any large truck, what is it that's behind that back axle? It's behind the tire. Shocks are actually on the chassis itself. They move like this, flap in the wind. Something flaps usually. Yeah, mud flaps. Okay? So that's the reason that those are behind that vehicle. Okay? Because as that's rolling down the road, okay, so if a rock or anything like that, if it comes out of that tire tread at the top of this track, then it just goes shooting straight like this, hits the mud flap, and down it goes. So if it breaks loose here, just as long as it's, I don't know where it would possibly be that could be a problem. But I suppose even if it hits the ground, it's still going to go tumbling down the road, but at least it's not coming straight at you. I mean, that still might happen, but that's what leads to a chip in your windshield. But that's why you have those mud flaps on there, is ideally rocks should hit the mud flap and then fall straight down to the ground. Okay.
Is that going to be on our exam?
We're going over it. Maybe. Okay. And let's see here. So then we were talking about this earlier as well in the morning session. So if we had, I think I use Hulk hands here. This guy. You probably saw Dallin walking around with this during homecoming week. Okay? This is much, much bigger, and it's heavier than this marker. Okay? So which one would hit the ground first? Same time. That's right. So didn't earlier we say that regardless of the mass, they should hit the ground at the same time? That's true. Maybe. But if that's true, why did the Kleenex not fall? We said it earlier.
No, it says the math doesn't matter.
The mass doesn't matter. Okay, you're close with shape.
Material.
Well, what's hitting that surface area?
Gravity.
Air resistance. That's right. Okay. So what what do we want to say about that? It was the idea of if anyone sees the write-ups on Facebook after a cross-country meet, always put the same two words at the end of every write-up. Why is that? You just remember that?
Yeah, before every race. You would say that?
I don't know if it would be during, maybe not before. Was it? Maybe it was.
You would say something about see if the finish line hangs up or something.
No, I'd say be safe, have fun, and we'll see you at the end. Then during the race, we would say, hang tough. It's nothing that I came up with on my own, like we talked about in the morning session. Does anyone know when D-Day was?
Yeah.
June 6th,
Oh.
1940 what? 1944. Okay? So that's when we liberated France, you could say. And I think...
I was thinking about USD.
Okay. So that, yeah, Dakota days. But anyway, with that, I suppose you could say that our debt to France was probably repaid, because when you go back to their revolution, that's how I think the British didn't escape Yorktowns, because the French cut them off. Now we repaid them back in 1944. But anyway, so you have all these paratroopers that are in the 101st Airborne or 82nd Air, I don't know which. But with that, you had Captain Winters, I think was his name, Lieutenant Captain, Major, something like that. He has all these soldiers that are in his platoon. They're about ready to jump behind enemy lines, so you can about imagine. To me, it's frightening enough just jumping out of a plane, but maybe some of you'd want to do that to parachute, okay? But I think if we put that into perspective, where you're going to jump off this parachute into enemy lines, there's probably some anxiety that would arise from that. Okay? But Captain Winters, I think that was his rank, said two words that really calmed his soldiers. Hang tough. Yeah, so that's what he told. It comes from Richard Winters. Yeah, like I said, I can't take credit for that. Anyway, so how is it that parachutes work? You have that coming down at a certain rate, so then the air resistance must match what's hitting the parachute, and that's why you don't keep on accelerating all the way to the ground. Okay? All right, and then I think that was about it. Then we went over a problem. Okay, so I'm going to hit pause here for just a moment. So I had taken this picture earlier, and that's why it has the answers on it already, so I just rewrote that. Okay, so we'll see if this makes any sense. We were talking about if you have like Saturday morning chores to do, like myself, we had wake up, go feed the cattle, take care of the hogs, and things like that. But anyway, want to get inside, watch Looney Tunes. Okay, so while turning a corner, Wile E. Coyote is moving at 45.25 meters per second. If he hits a wall with 1,584 or 1584.50 kilograms per meter per second, what was the mass of Wile E. Coyote? And what was his speed before he turned the curve if that time frame was 3.65 seconds earlier? What is the force on impact if he hit the wall moving at 8.75 meters per second squared? Okay, so now we're going to go ahead and continue. So you've read the problem for about the 22nd time now. I think we said that this morning. What is the next thing you should probably do? Okay, so what do we know in this problem?
Your final velocity is 45.25. Your momentum is...
But how would you know? That's right, but how would you know that?
Because it's turning a corner.
Okay.
And you're looking for your initial velocity.
That's right, because when we look at this, what was his mass? We're looking for that. Oops, that wasn't very good. What was his speed just before he turned? Okay. And then finally, what is the force? Okay. So what else do we know in this problem?
Your momentum.
How do you know it's your momentum?
Because it's of the label.
Okay. So what's your numbers then?
1584.50.
So since this is labeled in kilograms per meter over second, we know that that is a momentum then. Okay, what else do we know in this problem?
Your time,
Okay,
which is 3.65.
seconds. Okay,
And
that's not 0.655, that's a second. Okay,
and your acceleration, which is 8.75.
and how did you know it was an acceleration?
Because it has the 2 by it. Or
Well, yeah, that's
squared or
it's
something?
squared. Yes, it is a 2, but yeah. So anyway, so 8.75 meters per second squared. So we're looking for these. We need a force. Okay, it's looking for, since it says before, that's going to be an initial velocity, and then finally a mass. So we just put those down in just really no particular order. But can we solve for a force here?
No.
You're correct. We can't. Why can't you solve for force?
Your mass.
You don't have a mass. Can we solve for an initial velocity?
Yeah.
We can?
Yeah.
Are you sure?
Yeah.
Okay. You can solve for either one. You could go with mass or initial velocity. So which one would you like to see first?
Mass.
Okay. So you can also solve for your mass, but how can you do that?
You take your momentum divided by your final velocity.
Okay, so we're using the momentum formula. So we've got, 1584.50. So what's on the right-hand side of that equation now?
45.25.
Okay, is that it? No, also your mass. Okay, so then we have to divide each side by what?
45.25.
And if I remember right, I think it just comes to what, 35 even? Oddly enough, so mass equals 35 kilograms. Okay? So then, now that we have our mass, what's the next one we could solve for?
Find your force.
We can find our force.
8.75 times 35.
8.75 times 35, what we just solved for. And then we get, what, maybe? 300?
306.25.
Force equals 306.25 what, though? Newtons. Okay? All right. So then our final step, how could we solve for our initial velocity?
For your acceleration equals your final velocity over your time.
Okay, so it's 8.75. So what's on the right-hand side? We got a fraction.
Your time's on the bottom,
Okay?
and then you have your final velocity on top.
So do we know our final velocity?
Yeah.
Yes, we do.
45.25.
And then what's left over here?
Yeah.
Okay? Are we going to do what's inside the parentheses first? No, probably not. So probably the best thing to do would be get rid of your fraction. And how can we do that? Okay? And the simplest way to do that is like what we've been doing since last August. What is 1 times 45.25? 45.25. Running out of space here. What's 1 times VI? Minus VI. So then what's on the right-hand side of our equation now? Multiplying these two, that's right.
It's 31.94.
31.94. So we got to get that VI all by itself. We would subtract each side, but that gives you a negative value, though, don't it? It's also negative on this side. So if it's on negative on both sides, that means it becomes positive. So our initial velocity then is 6 something, 7 something.
Wait, what are you doing? Yeah.
How much? 15? 13. 3.1 meters per second. All right. There we go, with a couple of minutes to spare.
How long is our thing?
What about the mass?
You round it down, it should have been 35.02.
Okay, well, I don't know. I knew it was close to 35. Anyway, that's all I have. We'll catch up to you next time.